Hi everyone. Now we'll see the properties of the cross correlation function. Okay. So cross correlation. Okay. So in the previous video we saw the properties of the autocorrelation function. Autocorrelation, we're seeing the correlation between the, that is a similarity. Correlation means similarity between x of t, the same signal, shifted signal, x of t plus tau. Now cross correlation means we are taking two random processes. That is the relation or the correlation between the two random processes x of t and y of t. So whenever you come across the word cross correlation, meaning that the relation between the two random processes x of t and y of t. So as usual, whenever we are going for the properties of the cross correlation function, we are assuming that two random processes x of t and y of t are at least Wide-Sun stationary, jointly Wide-Sun stationary. Okay, that is the meaning. Previously we wrote x of t is at least Wide-Sun stationary. Now we are writing both random processes x of t and y of t are at least Wide-Sun stationary, meaning that the cross correlation function rxy of t comma t plus tau is function of only the time difference tau. Okay, so then the following properties of the cross correlation function. So while coming to the first property, rxy of, so we are writing the cross correlation is given by rxy of, rxy of tau is cross correlation between the x of t and y of t, notation for the cross correlation. So rxy of tau is equal to ryx of tau. This is ryx of tau. So this is a symmetry property. Now we know the formula for the, if you go for the proof of this one. Okay, so rxy of tau, how will you write? Normally previously if you remember what we wrote, rxx of tau, rxx of tau is expected value of x of t, x of t plus tau. We wrote this as formula. Okay, now we are having rxy of tau. That is what we need to write, expected value of x of t. Now I am having y instead of x. So write y of t plus tau. Okay, so that is the formula for the cross correlation between the x and y random process. E of x of t, y of t. Now, if I want to write ryx of tau, ryx of tau is, first we are having y, then we are having x. Replace like that. E of y of t, x of t plus tau. Okay, now replace tau with minus. Tau with minus. So what we'll get? Ryx of minus tau is equal to, wherever we are having tau, replace with minus tau in the above equation. So y of t, x of t minus tau. Okay. Now let t minus tau is equal to another variable u. Then what will happen to t? T is equal to u plus tau. Okay, so what we'll get, ryx of minus tau is equal to expected value of y of t. So what is t? U plus tau. So y of u plus tau, x of u. Okay, so you can replace u with another variable. Yes, it is a variable. So what I am writing, x of tau, y of t plus tau. So what is this one? Sorry, x of t, y of t plus tau. What will be r xy of tau. So r, therefore we can write it as ryx of minus tau is equal to rxy of tau. Okay, so this is the proof for the first property. Okay, now we'll go for the second. We are having rxy of tau and ryx of tau. Okay, so these are the rxx of tau and ryy of tau. are the autocorrelation functions of the random processes x of t and y of t respectively. Then the cross correlation between x of t and y of t satisfies the inequality modulus of r x y of tau is less than or equal to square root of r x x of 0 r y y of 0, where r x x of tau, r y y of tau are autocorrelation functions of x of t and y of t. Then the cross correlation, that is r x y of tau, satisfies the inequality modulus of r x y of tau is less than or equal to r x x of 0 and r y y of 0. That is r x x of 0 is the autocorrelation function of x at tau is equal to 0. R y y of 0 is the autocorrelation function of y of t at tau is equal to 0. So if you go for the proof of this one, okay, consider whenever we are having any inequalities like that, we need to consider one, consider this x of t by square root of r x x of 0 plus y of t plus tau divided by square root of r y y of 0 whole square. Okay, so if you consider this is looking like a plus b whole square. Always a plus b whole square is greater than or equal to 0. Okay, now apply the expectation on both sides. So if you apply the expectation, e of x of t divided by expectation is also greater than or equal to 0. Now you expand by using the a plus b whole square form. What do you get? That is equal to expected value of x square of t divided by r x x of 0, that is a square, plus b square y square of t plus tau divided by r y y of 0 plus or minus, here also it is plus or minus 2 x of t y of t plus tau divided by square root of r x x of 0 r y y of 0 is greater than or equal to 0. Now you came to know that why we are taking here root of r x x of 0, here r y y of 0, because here we are having r x x of 0 and r y y of 0 in the inequality. That's why we are taking the square root of r x x of 0 and r y y of 0 here in the denominator. Now what will happen? Apply the expectations correctly. So we can have the properties of the expectation. We can apply the expectations correctly. R x x of 0 divided by, if you r x x of 0 is constant, you can take outside. E of x square of t by r x x of 0, e of y square of t plus tau divided by r y y of 0 plus or minus 2. So you are applying expectation for x of t, y of t plus tau divided by square root of r x x of 0, r y y of 0 is greater than or equal to 0 total. Now if you see what we are having, e of x square of t. So if you remember the properties of the autocorrelation function, first property, e of x square of t is equal to r x x of 0, that is the autocorrelation function at tau is equal to 0, mean square value. Mean square value is equal to the autocorrelation function at tau is equal to 0 from the first property, that is we know that e of x square of t is equal to r x x of 0, and similarly e of y square. E of y square, either it may be t or t plus tau, it is also equal to r y y of 0. That is e of y square of t plus tau is equal to r y y of 0. Substitute these two there, what will get? That is equal to r x x of 0 divided by r x x of 0 plus r y y of 0 divided by r y y of 0 plus or minus 2 e of x of t y of t plus tau. That is nothing but the cross correlation, that is r x y of tau divided by square root of r x x of 0 r y y of 0 is greater than or equal to 0. So this becomes 1, this becomes 1. So 1 plus 1, 2. 2 plus or minus 2 or xy of tau divided by square root of rxx of 0 or yy of 0 is greater than or equal to 0. We divide with 1, sorry 2, what will get 1 plus or minus, that 1 will get cancelled, r xy of tau divided by square root of rxx of 0 or yy of 0 is greater than or equal to 0. So what will get plus or minus rxy of tau divided by square root of rxx of 0 ryy of 0 is greater than or equal to minus 1. This 1 will become this side. So what we can write plus or minus means, I can write this as modulus. Modulus of rxy of tau divided by square root of rxx of 0 ryy of 0 is greater than or equal to minus 1. If you multiply, what will get rxy of tau modulus is greater than or equal to minus square root of rxx of 0 or yy of 0. If I multiply with minus, what will get rxy of tau modulus is less than or equal to square root of rxx of 0 or yy of 0. Okay, so this is the second property. That is, the modulus of the cross correlation function is always, that is the absolute value. Modulus means absolute value of the cross correlation function is always less than or equal to the geometric mean. If you are having x and y, root of xy can be called as geometric mean. Okay, geometric mean of the autocorrelation function of x of t and y of t at tau is equal to 0. This is the second property. While coming to the third property, this is rxx, rxx and ryy are the autocorrelation functions of the random process x of t and y of t respectively. Then the cross correlation function satisfies the inequality or xy of tau modulus is less than or equal to half rxx of 0 plus ryy of 0. Okay, so if you go for the proof of this property, so we said that in the previous one, this is a geometric mean, root of xy is the geometric mean. If you go for the arithmetic mean, x plus y by 2 is the arithmetic mean. This is the arithmetic mean of the two values, and x and y, and the root xy is called the geometric mean. Okay, so if you see, geometric mean of any two positive numbers cannot exceed their arithmetic mean. Okay, geometric mean of two random cannot exceed arithmetic mean. Okay, now you consider rxx of 0 as one value and ryy of 0 as that is the two positive quantities. Okay, consider rxx of 0 and ryy of 0 as two positive quantities. Okay, then what we are having the geometric mean, we are saying that geometric mean cannot exceed. Mean is always less than or equal to. Geometric mean is always less than or equal to the arithmetic mean. So geometric mean between those two is square root of rxx of 0 ryy of 0 is geometric mean between the two is always less than or equal to arithmetic mean is rxx of 0 plus ryy of 0 divided by 2. Okay, so geometric mean is always less than or equal to, take it as equation 1. Okay, so in the above property, what we are having, modulus of rxy of tau is less than or equal to what we are having in the previous property, modulus of rxy of less than or equal to the geometric mean, that is square root of rxy of 0 ryy of rxx of 0 and ryy of 0. Take this as equation 2. So what we can say from 1 and 2? Always from 1 and 2, I can say that modulus of Rxy of tau is less than or equal to, that is half of, we are writing like this, Rxx of 0 plus Ryy of 0. Okay, that is our property. Okay, so whenever you are solving the second property, remember that always geometric mean cannot exceed, that is less than or equal to the arithmetic mean. So from 1 and 2, from the previous property, you can write that mod, that is the modulus of Rxy of tau is always less than or equal to the arithmetic mean of those. Okay, now we'll go for the fourth property. Okay, two random processes x of t and y of t are statistically independent. They had given the conditions that if x of t and y of t are statistically independent and are at least Wardson stationary, then Rxy of tau, Rxy of tau is equal to x bar dot y bar, where x bar is the mean of the random process x of t and y bar is the mean of the random process y of t. So if you go for the proof of this property, okay, so two random process x of t and y of t are at least Wardson stationary. So if you write the property for Rx, that is the formula for Rxy of tau, that is what we can write. We are assuming that it is a Wardson stationary, so we can write it as x of t, y of t plus tau. This is the formula for the cross correlation of x and y. What they had given, since they had given that x of t and y of t are statistically independent, are statistically independent, what we can write if they are independent? E of, so if two random variables are independent, you can write E of xy is equal to E of x into E of y. Okay, so same way here what we can write, Rxy of tau is equal to E of x of t into E of y of t plus tau. Because they are statistically independent, we can write it as E of xy as E of x into E of y. Okay, so that is equal to, what is E of x of t? X bar, E of y of t bar, y bar. So therefore, Rxy of tau is equal to x bar into y bar. Okay, so whenever you are writing the property, you need to write both these are the Wardson stationary and statistically independent. So write the formula for the Rxy of tau, statistically independent, E of xy is equal to E of x into E of y, then E of x of t is the x bar and E of y of t. That is the Wardson stationary, one of the condition for Wardson stationary. One of the conditions is the mean value is x bar. Okay, so next if you go for the fifth property, if two random processes x of t and y of t have zero mean and jointly Wardson stationary, then limit tau tends to infinity, Rxy of tau is equal to 0. So if you go for the proof of this one, what we are having, x of t and y of t. Now we'll write the formula for Rxy of tau, that is equal to E of x of t, y of t plus tau. Okay. Now, what they had given, limit tau tends to infinity. So now take the limits on both sides. Limit tau tends to infinity, Rxy of tau is equal to limit tau tends to infinity, E of x of t, y of t plus tau. Okay. As tau tends to infinity, the random processes x of t and y of t are statistically independent. That is the rule. As tau tends to infinity, x of t and y of t are statistically independent. Statistically independent. So if they are statistically independent, what can I write? Limit tau tends to infinity, E of x of t, I can write separate E of xy as E of x into E of y. Okay, so E of x of t, E of, you can remove this one, t tends to infinity, then they are statistically independent, E of x of t into E of y of t plus tau. What they had given, zero mean. So it is 0 into 0, that is equal to 0. Okay, if you see the fourth and fifth property, they are almost same. Here they are given as tau tends to infinity. So as tau tends to infinity, x of t and y of t are statistically independent. That's why writing e of x of t, y of t is separate. 0 means substitute mean value as 0, so we will get it as 0. If you see the previous property, instead of saying that tau tends to infinity, they themselves had given that it is statistically independent. And they didn't mention that 0 mean. That's why we are writing x bar into y bar. That is the difference between the fourth property and fifth property. Okay, so these are the properties of the cross correlation function. Thank you.